Okay, now we want to talk about what happens during address translation, and this leads to a discussion of translation lookaside buffers. The addresses that the CPU generates are virtual addresses. They correspond to locations in virtual memory, but of course we need to refer to the physical memory locations where those addresses are located. So we have a page table, and the page table tells us where the virtual address points. It takes the virtual address page number and tells us what's the physical page frame address where that memory is found. But we can't afford to access the page table in every reference because it's too slow. So instead we use a translation lookaside buffer, or TLB, which is like a special cache that's indexed by page number. If you're accessing a page and there's a hit, that means that the page is in main memory, and then you immediately obtain the page frame address. But if there's no hit in the TLB, well, the page may still be in main memory. You just need to go out and look at the page table to see if it's actually in main memory, but that means doing it the long way and making an actual memory reference to the page table, and that takes a very long time. So diminishing that time is an area of active research, but we won't go into much detail on that today. So what this means is that the TLB needs to be accessed before you know the physical address, and therefore before you can access the cache. So we translate our virtual address to a physical address through the TLB. Then we access the cache. Either there's a cache hit, in which case the cache returns the contents of that location, or otherwise there's a cache miss, which means we go to memory. Well, this adds an extra cycle even if there's a hit, because you've got to go through the TLB before you can even start the access. So to save this time, let's look at what happens when a memory address is accessed. In the diagram here, you can see that there's a virtual address up at the top, and that virtual address needs to be translated to a physical address. The virtual address is divided into these three fields: tag, index, and offset. Whatever in the tag field is compared with the tags in the set. And which set? Well, the index field is used to select which set we need to look in, and then the offset field determines where in that cache line you look to get the information. So now I have a question for you. Here I've listed 7 steps in cache access. I'd like you to reorganize them in the correct order. Okay, now that we have the steps in order, let's look for opportunities for concurrency. The last 4 steps need to be sequential because you can't select a line before it's in the sense amplifier. And you have to select a line before you can choose the bytes to return. But there is opportunity for parallelism earlier in the process. If we knew the if we knew the index before address translation started, we could perform some steps in parallel. Now, there are the steps numbered in order. We could perform steps 2 and 4 while address translation is occurring. That is, we could access the set that could contain the sought-after address, pull down the tags into the sense amplifiers, and read all lines into the sense amplifiers. But there's a trade-off between power and speed. If we want to save power, but we don't really care about speed and none of the tags matches, then we don't have to read any lines into the sense amplifiers. So we could skip step 4. But if we want maximum speed, then we pull down the tags and read the lines while we're comparing the tags. In either case, if there's a match, we return the bytes to the processor, and if there is no match, then it's a cache miss, and it has to be handled by referring to main memory.